So as I was saying, my last presentation taught me that most of the efforts were in the first half of your projects, that is the selects. To get the ephemeral seemed to be most amount of work. And so that taught me that there was something missing there. So that's what led me to what I'm going to show you here.
Oh.
Try it over here.
No. You should be good. It should click.
Yeah, it works. Okay. Just a side, that's it. So today, and I don't have to dwell on this, this is what the state of the process of getting ephemeral is. And now we think this was the new age of aptamers when you can make them in silico on the screen in minutes, validate them in days, order them and start working within 2 weeks, which is a remarkable difference between where we are today and what this will do. And this is doing. So it is a completely computational process. It gives you a sequence, morphology, where the aptamer is binding to the target molecule, atom by atom, position by position, and with affinity, cross-reactivity, and all the properties that you like. Without doing the analysis after you get the aptamer, you build it, therefore you know everything. So if you have a biomarker, you get an aptamer in your lab in days. This was, all the images I'm going to show here were done by the software. All of those within 60 minutes. In our configuration, we're always showing the aptamer in blue, and the sort of golden bronze is the target molecule. The first one we did was these are the applications that you can use them for. Obviously, you know more about this than I do, and I'll move on to this. So the way we do the aptamer synthesis is fundamentally to select the region of the protein, if it's a targeted protein. This reduces the computational budget. That's all it does. So if it doesn't work or you don't get an aptamer you like, you can choose a different region. So after 2 more coffees, you get the result again. So that's all there is to it. A lot of the simulations were also done, especially the second stage, where the solvent or the medium in which it is going to live is described, and you can decide what the medium is. Number of docking runs that you have to do will determine how accurate the results are going to be. So the way we do this, and this is our contribution to the science, we have something called short aptamer sequences. These are 4 nucleotides, and all the possible combination of those, and they end up being, which I will show you here. This is the algorithm just for the synthesis. Start with 4, you get 256 different permutations. Take out the ineffective permutations. So, and for each SAS, we have about 20 poses. Within 1/20th of the 363D space, they are free to adapt. Therefore, 20 poses. So you have 4,800 different short aptamer sequences. Each one we take and bind to different places in the selected region of the protein. At the end of this, which takes minutes, you end up having a class of short aptamer sequences that binds in order of affinity. So we call it a docking score for a reason I can explain later. And in the end, essentially, we then go and see whether which SAS is competing in 3D space with the other. So now you have a different class, a subclass of SASs which are not competing in space. They're free to be connected. Then we go and connect them with linkers if they're too close, about 10 angstrom, and with connectors. And these are created in real time as the process is going on. So we link and connect SASs together to form the complete aptamer. So these are the stages. So you have, for example, this is the alpha syn. This is the alpha syn protein, a section of it, because it's just about long. And this was given to us by the Montreal Neurological Institute. We would have researchers working on alpha syn for Parkinson's. Those are short aptamer sequences. So the binding with the linkages and the etiquette. So the further steps after the synthesis are validation or folding properties in the right medium. And the medium we declare the constituents of the medium. Then the 3D visualization of the binding site like this. And you can expand it to look at every atom, which one is binding where. And depending on the type of visualization you have, you can see it better or less. These are standard visualizations. Then the next module we have is a circle for binding dynamics. And we're using open source software which has been tailored to be specific to this application. So the user doesn't have to know these 100 different open source software and how to use them. We have confined them into the pack. And then, of course, in the end, you want to know your cross-reactivity. There, the major challenge we have is how do you choose the molecules you're going to test it against? Millions of them, 10 of them, 5 of them, but you can check each one depending on the computing budget you have. And I'll give you the numbers here. Synthesis takes less than 90 minutes, sometimes only 10. The major problem we have found in synthesis is not the synthesis itself, but making sure the molecule that you are giving it as a target, its description is complete, or at least complete in the area you want to attach to. And we have found many of like alpha syn was not complete. The p-tau 181 for Alzheimer's is also not complete. And the incompleteness comes from, most likely from X-ray photography, which could not determine the 3D coordinates of each atom, or not certain enough of it. So that's usually a mistake. But it's not a major problem because most of them are detailed enough to be able to synthesize. Now, the advantage, as Dr. Fawn at MNI said to me, that at this rate, I can make a mistake. If I can do 4 aptamers by the evening, so what? It didn't come out right. It'll be small. The folding validation is 10 to 30 minutes, depending on the size. The binding validation is 20 to 40 minutes. Stage 4 and 5 is what can take days, especially for, and the cross-reactivity assessment takes about 60 minutes, but let's say you're doing 10 or 20 molecules, it'll end up in a day. So essentially, in about 4 or 5 days, you have all the data you want for the aptamer you have synthesized. Now, obviously, it has not been tested at this stage. You have a sequence, you have all the information, but now it has to go through the lab test. But not to determine it's the right aptamer, just whether the properties are as predicted. Now, like any software, in the beginning, it will have its failures. There will be defects, there will be shortcomings, there will be lack of functionality. But in a few months, all those will be solved and new ones will be discovered. And this is the nature of software. If you remember what Word was in 1991, at least I remember 1991, and what it is now, because time is very, very critical in the quality of software. So we are not claiming that this will solve everything tomorrow morning. But as a tool, we will get there. And even today, we have been able to do multiple. Yes, and this is a comparison of where we are with Cellex today and what Aptosoft will do. And we have demonstrated this. So this changes part of your work that is about finding the aptamer. And for this, I have to thank Professor McKee for guiding us and this society for guiding us as well to get here. As you can see, this is what we are able to do. I don't want to speak about AI in the field of aptamers, mainly because I don't think much of it. And there's reason for it. And first, I belong to the AIM in the first wave of AI, which was 1969, 1971, with Marv Minsky in MIT. I was not part of the main group, I was on the borderline, but I saw why it did not succeed. The present wave of AI will succeed in some way. But like any other idea, when it occurs, it's the best idea ever, it'll solve everything, heaven is coming soon. Unfortunately, that never happens. Self-driven cars were supposed to be here 5 years ago, and now nobody talks about them. The failure was in AI, mainly. And so our assessment is that AI will help us find the most important molecules to select out of the millions for cross-reactants. Because the mistake there will not be horrible. Because AI fundamentally depends on probability, and computational chemistry does not. It is deterministic. And there lies a fundamental difference in the two approaches. So we chose not to go in there. This is our association with the NEO, Montreal Neurological Institute. It was funded originally by the Rockefeller Foundation in 1924. I was on the board for about 12 years. And so we are working with them on Parkinson's, Alzheimer's, Lou Gehrig's, because they have the biomarkers. We don't. We have no idea how to find a biomarker, what they are, and whether we can trust them or not. So they have the research team in different sites, and essentially this was done in between 10 o'clock and 12 o'clock at noon. And this is the alpha cell. Now we have to give some more details to the protein description, the protein database. We hope to get to one single drop of blood testing for Parkinson's by the summer, using our devices, which I will show in a moment. And We are providing them aptamers for ALS, cognitive disorders, whatever they ask us, we do. Similarly, we are working with the Jewish General in Montreal for troponin. And the Quebec government is funding a program across the province for very, very high, very low concentration of troponin, which is now a sign of an 18-month pre-diagnosis of women's heart conditions, because women's heart conditions do not have ulterior symptoms like usually men do. So there's a program for a 2-year study using our devices and technology. And here we go with this. Oh yes, we saw a Roche announcement of a DNF aptamer for p-tau 18140. I gave it to my team, and by the lunchtime we had this. So we think it's a new paradigm for work in the aptamer field. And we hope that this will accelerate all the development of aptamer applications. Along with this, we have to say thank you. And anybody who wants more information, please email us. We are also going to have some webinars. So people who have more knowledge than I do will be able to answer questions that there might be. We'll be offering this to institutions in research and universities at a very low rate of connectivity. We are not going to be selling the software because of security as well as support issues. And till we change, that's the way we will be doing. And for commercial organization, of course, there'll be a different. So thank you very much.